Hello everyone, welcome back to this ACC session. And the first speaker is going to be Mitch O'Reilly, who will present how learners are formed.
Okay, thank you very much. And thank you to the organizers for this conference, which has been great so far. Okay, so I'm going to present what I think is a nice observation about the category of learners. So I actually don't remember if there's been a talk involving learners so far this week. So I'll just remind us of the definition. So this is from the original paper by Fong, Spivak, and Tuyeras. So we're going to work in a category of finite products. A learner is going to be a choice of an object of parameters P, and then the following collection of maps. So the first one, and this is supposed to correspond to some kind of machine learning algorithm. So the first map is somehow we have an input A and we're predicting a B based, using the parameters. The second map is this update map where if we have, the correct answer for an A, we can update our parameters and try and improve our improve what the learner knows. And the final map is this request map, which is a little more mysterious, but is necessary to make these things form a category. So in the specific case of like a gradient descent learner, this is somehow transmitting information backwards about the partial derivative of the error with respect to the input. Okay, so I see this definition and I'm wondering, well, first of all, why these particular maps? It's sort of maybe an odd asymmetrical thing. And the fact that it works is a good answer. Maybe that's fine. My second question is, well, we have to do this quotient of these learners up to isomorphism of the parameter object. We have to do something here because if we don't take some kind of quotient, then these things don't form a category because associativity fails sort of for annoying reasons, which is just that like the product isn't, the categorical product isn't strictly associative. So we have to do some kind of quotient on these things, saying when learners are equal. But why just isomorphisms? And I mean, in follow-up work by Fong and Johnson, they say, no, actually, we're going to do a quotient up to any surjective map at all. And that also seems useful, but also why that? And there's been some work which has sort of decomposed learners into the combination of simpler things. So this a category of learners like this is almost paralens. There are some differences, like the object here and the object here don't have to be the same, and they compose differently. But I'm going to take a different path. Okay, so I'm just going to write the data of a learner on the top line here. So here we've got our three maps that we had before, and this quotient up to isomorphism of parameter objects, we can phrase it as a coend over all of the isomorphisms in C. So now I'm just going to manipulate this. So first of all, we've got two maps out of the same object, so we can just combine them, universal property of the product. Now I'm going to use just some coend calculus. I'm going to do unitative reduction in reverse, and I'm going to take this copy of PA and sort of pull it out into its own map. And this will be the same because I'm taking the coend over Q, which will stick it back in here. So these are isomorphic. And then once again, I've got two maps with the same domain, and I'm going to glue them together into a single map like this. And we end up with just the data of a learner in the original sense is the same as the data of an element of this coend. Now, I'm just going to copy this to the next slide, hopefully, if this goes. Yeah. So this is just the last line again, no changes. And already there's something nice about this, which is that the actual maps involved here are like, it's like completely symmetrical between these two things. But there are some obvious things once you get to this point to try, and I'm just going to do all of them, which is, well, first of all, there's this asymmetry between the categories that we're taking the coend over. So the first thing I'm going to do is I'm just going to say, why not just take the coend over all of C for this one, make it more symmetrical. Then in this form, there's no particular reason that the product in here has to be Cartesian, so I'm going to change that. And then finally, I'm going to do the same move that happens for regular optics, where the input objects and output objects don't have to be exactly the same. So over here, I'm going to give these primes. And now this expression which we've come up with will be the definition of learner which I'm going to use. And forgive me, I'm just going to call these learners because I'm not going to talk about the older version. An alternative name for this could be symmetric optics or something like this, favored by some people in the crowd. But I'm just going to go with learners. So when we choose the monoidal product in here to be the Cartesian product, this is almost the original definition because we can unwind a lot of the moves that we made. But we are equating these learners up to a more generous equivalence relation than we were before, because up here, it's no longer just isomorphisms. So more learners become equal. So what I want to do is show you what this relation looks like. So this is the original one for when two learners are the same. We've got two pieces of data up here, and they're the same when there's an isomorphism of parameter sets, so that isomorphism, so like all the structure commutes with that isomorphism. So the triangles are clear, and then over here we have this commuting square. And in the new relation, now it's no longer an isomorphism. It's any map from P1 to P2, but we have to be careful when we unwind what the coend is telling us is equated. So these stay the same, but now for the update map, we need not just that there's a square like this, but there's a diagonal here, and this is just unwinding the dinaturality from the coend. Okay, what's next? Okay, so up here, this is just the same definition again. I'm going to keep putting it up there so you can look at it if you want to. How do we think about these things? These are now sort of, I mean, it's this strange set of things. I'm going to draw these as a formal diagram that looks like this. So in this coend, we can just pick a representative of the learner that we're interested in, and say the two maps are L and R. And I'm going to draw this as a diagram like this. I should be clear that this is not actually a diagram which is really happening in any category. It's just very sort of suggestive that we've got the left map here that takes in P and gives back Q, and then the right map here sort of facing backwards, which takes in Q and gives back P. And the coend relation is exactly saying that if we have a map which just acts on the parameters on either side, so we've got a map down here, we can slide it to be a map up here, and those give the same learner. And the same over here, we've got a map up here, we can slide it around to the bottom there. Okay, so here we can get, just looking at these pictures, we can get some really easy inclusions of other things. Well, first of all, the original category that we start with can be included into learners just by sticking it on the bottom here and then putting the monoidal unit everywhere else. And we can also see pretty easily that we can include optics into learners. So we start with an optic, I'm sorry, I should have put the type of the maps here, but again, they have a left and a right piece. And here, an optic it doesn't use this extra input, which we get out of the coend, so we're just going to stick a monoidal unit there, but it still uses this other side to sort of transfer information from the left to the right piece here. So we have these inclusions. Now, I didn't say, but of course, the learners, the way that I've defined them here, do form a category. They form a symmetric monoidal category, which I'm also going to call learn. And you can define what the operations do just sort of by following your nose. Like you want composition to do this, like we've just got them over here, and we stick them next to each other. But of course, this is not in the shape of the formal diagram that I promised you. And so what you actually have to do is like take this thing and drag it through, and take this thing and drag it through. And so really the definition of composition is like that. And then the new right piece is like you take the top part and chop it off, and you take the bottom part and chop it off. And those are the two maps. And the monoidal structure is similar, but the diagram is bigger and more impressive and doesn't fit on a slide. So I can show you later if you want to see it. Okay. So the kind of learner that we started with, which is built out of like a set and these three maps, is represented in this form like this. And I feel like this is quite intuitive. If we get some input and we've got the parameters coming in, then we can use our inference function to get output. But then we also copy these and save them to use it in the backwards pass. So we save the parameters and an input that we got, and the other maps are exactly what we need to get the A prime and a new P to feed in for the next thing. Any sort of the force of the manipulations that we did at the beginning are saying that any learner in my sense in a Cartesian category, so this should be just a Cartesian product, any learner in a Cartesian category can be rearranged to be in this form if you want. Okay. Now, right. There's something that cool that comes into view just because we've got this new incredibly symmetric formulation of learners, which is that there's a strict symmetric monoidal involution from the category of learners to itself. So from learn op to learn, where we just take any object and we flip the two sides, and we take any map and flip their roles in the learner. So in terms of a diagram, we're just taking it and then turning it upside down. And clearly, if we do this twice, we get exactly back to where we started. So this, for Cartesian learners, we can go back and unwind what this is actually, what this is doing to them. So this operation must exist in the Cartesian case as well. So I know it's a lot of symbols, but I'll just try and explain it. This is just what you get by working through it. There's nothing magic happening here. We start with our original learner up here. We do the dual once. The new parameters are the old parameters cross A. And then if we want the implementation function, we have exactly the data we need to feed it into the response function from the original learner. And the update function here will use the remembered A to do an update and then save the new A for next time. And the response function is sort of similar here, where we have the data that we need to do the implementation function from the old learner, except we now also do the same update in here. And if we do this twice, we get the following. We get a version of the original learner, except where it has remembered a new piece of data, which it will like pre-update on every time you do some operation. So here, when you do the implementation function, it will do a little update on the remembered data and then do what it was going to do anyway. And that's the case for all of these pieces here. And so this learner is under the new relation equal to the old learner. And what we need is a map between parameter sets, which shows that this is true. And the map that we want is a map from P cross A cross B prime, just down to P. And we have such a map. It's exactly the original update map here. So the update map here shows us that this double dual learner is equal under this new relation to the original one. Okay. Well, what else do we have in this category? So we have we'll just take an object where we stick the monoidal unit in one side, so just an object from the original category. We have this is a cup, which we can define just like this. Again, we just need to choose morphisms that we put here, and we can choose the ones that like takes in an A from the top and then just immediately supplies it at the bottom. And we can do the same thing for the cap, just sort of taking the input in here and feeding it back straight around here. So to summarize, we have a category, a symmetric monoidal category with an involution, and every object has a cup map and a cap map. So is this category compact closed? And the answer, I mean, obviously, given the title of the talk, is no. And what's missing is that when you compose the cup and the cap for any object, the snake equation tells you that this is supposed to just be the identity on that object. And that's just not the case in this category generally. If you compose those things and cancel a bunch of monoidal units and simplify as much as you can, you end up with a diagram like this. And there's just no reason for this to be equal to the identity morphism. And if you've seen any of the papers on feedback categories versus traced categories, where exactly saying that in this category, we don't have like a yanking axiom. We can't pull this kind of loop through to be flat. And so one final time, what does this mean for Cartesian learners? Well, this is the Cartesian learner where the parameters are just A. If we do the implementation, it gives us back the remembered one. And if we update, we just stick in the new one. So yeah, there's no reason for this to be the identity. Okay. So from our category of learners, I'm going to define a new category where we just quotient the morphisms so that all of those snake equations are equal to the identity morphism. And if you do that, you get what I need a better name for this, so if anyone has any suggestions, I'm going to call it atemporal learners. So learners where this sort of delay going around the loop doesn't exist. So this category is compact closed. That, like the snake equations, really was all that was missing. Well, actually, not quite. So once you have the snake equations, you just need that the cup and the cap, which we defined, which we saw on the previous slide, are extra natural with respect to all of the maps in the category. And for some of the maps, this is really easy, because if the map comes from C, then the sliding equality exactly tells us that we can like go around the cap. So certainly those are equal. But what we need is that every morphism in the category can be slid around the cap. And it turns out that just having the snake equations, you can fiddle around a bit, and that's enough to get everything. Okay. Okay, so not only is atemporal learners compact closed, they're in fact the free compact closure of a symmetric monoidal category C. So just to state this formally, we've got these two categories of symmetric monoidal categories, monoidal functors and monoidal natural isomorphisms, and then compact closed categories, monoidal functors and monoidal natural transformations. And then this construction takes us from any symmetric monoidal category into compact closed categories, and this is left bi-adjoint to the inclusion going the other way. Right. So learners aren't free compact closed, but they are almost free compact closed. So how does this proof go? Well, our strategy is to show that this inclusion here of the category that we started with into these atemporal learners gives an equivalence of categories like this. This will show that this is like a universal morphism. And for here, there's a trick, which is that all of the learner diagrams that I've been showing, where we pick a representative and then draw it like this, I'm going to take a diagram like this and then actually interpret it in the category of atemporal learners. And we can do that because it's a symmetric monoidal category. It has an inclusion from the original category, which is where this LNR live, and it has cups and caps, which we just showed. So we're taking the formal diagram and interpreting it in atemporal learners. And then what we need is, like once we decide where just the C part goes, like these morphisms individually, once we decide where they go, the fact that we end up with a compact closed functor up here means that where we send everything is forced, right? So that's the idea. All right, so this is not the first time that the free compact closure of a symmetric monoidal category has appeared, because you can get it by composing two results from the literature. We heard about this first one a couple of days ago in Eleanor's talk, where we can go from any symmetric monoidal category to a feedback category. And then over here, we saw this one in Samson Abramsky's talk, the in construction. And then what's missing? Well, the thing which goes from a feedback category to a trace category is you exactly quotient the yanking axiom to say that you have you can build loops and feedback categories and you just force them to be the identity. So the same kind of move is happening in both of these constructions, which I think is kind of interesting. Yeah.
Can you back up 2 slides?
Maybe, yes.
Yeah, so it seems to me your construction is slightly stronger than this is saying, because you've got a node pattern which already has a star, right? And you're really making compact close in such a way that the star becomes the compact close star.
Well, not quite. So unfortunately, I need to think more carefully about this, but the morphism that you get by like the duality on morphisms that you get by like composing it with the cup and the cap is not strictly the same as the one you get just by swapping the two sides. And so the compact closed structure that you get is not, it doesn't preserve that that star. Okay. Am I going down? Yeah. Okay. Right. Okay. Now, I went kind of fast, so before I stop for questions, I'll just ask a bunch of questions of my own, and then if you have any ideas, you can come and talk to me. So I'll preempt anything that you have to say. So if we don't quotient by this coend relation, depending on exactly what I mean by that, you could get a bicategory or a double category. And does that have a universal property? I'd like to know that. This is Mario's question. Does every feedback category embed faithfully into some kind of almost compact closed category where we have these cups and the caps, but they don't, I mean, we don't have this yanking? Is there a way to phrase this in a sort of profunctory style, the same way that you can get optics as certain morphisms of Tambara modules? It's not really clear to me what a Tambara module for this kind of thing would be. That would be fun to look at. If you have two learners which are just handed to you as maps, how can you test whether they're equal? This seems pretty difficult. Even before you do this extra atemporal quotienting, it seems kind of hard to tell when there's going to be some combination of sliding which will get you from one to the other. Next, is killing this delay a bad thing in practical applications? So people who actually do this should come and tell me whether they actually want to keep the delay around. Maybe it's good to remember. And finally, now that if this thing has a compact closed structure, how can we, does this help us come up with a nice language for like or a syntax for specifying learners? That's something I would like to know about. Okay, so there you go, that's the end.
So thank you for the talk, Arthur. Yes.
I have a bunch of questions. One is, I'll say a bunch of you pick. You know what the dual break descent does? That's one. And two, I think if you do this to a trivial middle category, you get one top, or that's enough word movement or somehow the complex category. So what do you, I don't know, TQFT something, I don't know, question around there to remind you.
If you do this to the trivial category, or would you need like the free monoidal category on one object or something like that? I mean, the trivial one would give you the trivial category again.
I mean, the terminal category. You get one for
I'm not sure. We'd have to think. And I feel the question. I also haven't thought about what the dual of gradient descent does, but that is also a very good question. Yeah.
So I know there is an excerpt in the third bullet point that program
Okay, great.
uses construction like a triple Tambara module to split things apart, and then everything but super symmetric. I can show you the well.
Great, fantastic. Yeah.
Okay, so I believe the Ruben Prakash had this notion of the nuclear ideal, which is like has a category which has not a subcategory, but an ideal where things act as if they can be like create the compact closed state, but it's not a subcategory. In particular, the identity. You know, this is of that.
The identity can never be bent.
Because it's not a subcategory, it's just an ideal. And there's some follow-up work on where they use this construction of conformal with
Yeah,
I was wondering if you know that this is this about?
I'm not sure. I think that up here to make almost compact closed, to make sense of that. I mean, in this case, the learner's on its own. You can't push every morphism around the cup and the cat. And so to make sense of almost compact closed, you would have to pick a subcategory where you're allowed to do that. I'm not sure if that's related. So I don't know. Oh, okay. Maybe. So I don't think I can.
Okay, so if you can take two those which page you look up you like and then identify them and then
Mhm.
I feel like that has the potential to be
Yes.
you know that this is
No, I have no idea. Yes, and that was one reason I'd love to know if there's some way of deciding whether these things are equal. Yep.
I think I meant the three-nodal category in one.
Right.
Free drop instead of the terminal.
Right.
Um,
It sounds plausible to me
Yeah.
because there's not much you can do except, yeah.
You give this definition of learner, you show that preventing symmetric or constructive use of words. And you went quite happy with that, so you some quotient. But this original category, like, is that giving you a monad on symmetric nodal category as well?
I wouldn't be surprised.
Okay, so
yeah.
are the algebras for that monad in almost compact closed?
My guess is that's true. I mean, there's that original Pastro Street paper, which is sort of the origin of a lot of this optic stuff. And there it is the case that it's algebras for a monad. And I suspect it probably is for similar reasons.
We know that the construction could be three compact closed category and a straight nodal category. Is there any sort of similar relation that falls between like feedback categories and the categories of learners you defined before you go to them to get the A-temporal learners?
I'm not sure. This is sort of Mario's question, I think. Yeah.
The object in this category of as I tend to think of the first pair as arrows are facing in a direction.
Yep.
I tend to think of the forwards arrow as inference and the backwards arrow as back propagation. And so then in the second place, I think of the object as containing derivatives.
Mhm.
So what do you is it clear what that means then when you have a cap or a cup?
So in the original paper, there's nothing sort of inherently derivative-y about the backwards things. It's all in sort of the interpretation from smooth maps. And I similarly don't think there's anything inherently sort of derivative-y here. It is a good question because as I was saying it, I was realizing that it does feel funny to feed this straight in, but yeah, I'm not sure. Sorry.
So learn may not be compact closed, but
Mhm.
it's closed.
Ooh. I don't know that either. If it is, it's probably not for. It's probably for strange reasons. Is my guess. I don't know.
The useful thing in the learn context is the ability to split things because neurons kind of the axons split to lots of different things. The combined structure on the learner. And in terms of like cobordism, this would be kind of like two cobordisms that kind of can split or something. But I'm kind of wondering if you thought about chromonoids or anything of that sort.
I didn't. Yeah, I'm gonna have to talk to a lot of people after this. There's lots of good ideas.
Maybe it's like